Hey everyone, Katrina here, and welcome back. Today we're going to be talking about constrained optimization problems, and in particular, Lagrange multipliers. Please subscribe for more videos like these, and watch to the end to see the full example. Okay, let's go ahead and dive in. So we're going to be thinking about constrained optimization. I've had previous videos where we've talked about unconstrained optimization and finding an optimal solution using methods such as gradient descent, and I've also showed other optimization videos where we can analytically find a solution using the second derivative test. So if you want any background information, be sure to check those out. So today we're going to be considering problems on a specific region that is unbounded yet defined, and we have constraints that our problem has to abide to in order to find the optimal solution. So we're going to go through some terminology first so we can understand what we're talking about, and then we'll go through a theorem, what the theorem means, and then we'll go through an example using Lagrange multipliers in order to find an optimal solution and optimal value to our problem. Okay, so let's look at this terminology. So suppose that we have some function here, f of x, and then we also have these other functions, h1 of x all the way to hp of x. And these functions are continuously differentiable functions on some open region, like I mentioned, and this open region is going to be defined as D, which is a subset of Rn. So the subset of a real number is in the dimension n, and the dimension n, this correlates to the number of independent variables x. So if we have 1x, then we'd have R1, which is just the real line. If we have x1 and x2, we'd have R2, and so on. So remember that n is the dimensionality, and that corresponds to the number of independent variables x that we have in our problem. So now that we've defined our function f and our function h, which are continuously differentiable on our open region, we are now interested in solving the optimization program. So we're going to call this an optimization program. So you might hear this as optimization problem, but we're going to kind of consider this as program because this is very correlated and related to like machine learning problems where we're trying to find that optimal solution to reduce our error as much as possible. So even though this is like a mathematical take at this problem, we can always like relate it to kind of this machine learning or computer program that ultimately is an algorithm that's trying to find the optimal solution. So we're going to call this program P. So I'm going to relate to this concept of P later on in our videos. So essentially what this program is, what we're trying to do is we are trying to optimize our function f. So optimizing means that we're either finding a minimum, we're trying to minimize, or we're trying to maximize our function. And both of these is kind of the general term of optimize. So when we're finding a min or max or extrema, that means we're trying to optimize our problem. And since this is a constraint optimization problem, we are now subject to specific constraints. So that's where this subject to comes into, because these ones over here represent our constraints. Okay, so let's take a look at what this means over here. So this problem has n variables. Like I said before, those are independent variables. And in this type of problem, we're going to be calling these decision variables, or DV. And f of x up here, this is called our objective function. So that's the function that we are trying to optimize. And then these equations, h1, h2, all the way to hp, these are our constraints, like I mentioned up here. So we have a function that we're trying to optimize subject to specific constraints. And that's why this is constrained optimization. And furthermore, we have a defined region which we have to operate on. So the set FR, which is our x, which is an element of that open region D, which is a subset of R, subject to the straight line means subject to the following constraints. And that is known as our feasible region. So that means that we are constrained to this specific feasible region to find our optimal solutions and our optimal value. even though there might be a better value somewhere else, that's not an optimal value for us because we are now confined to this feasible region. So this feasible region, like I said, is x has to be on that region D that we specified at the beginning, and further it has to be subject to the constraints, which are h functions, which we've mentioned in our optimization program. So the goal of our optimization is two-faced. So the first goal that we're looking at is to find these points, which I denote as x star, which are an element of our feasible region, which yields either the smallest, which would be a minimization problem, or the largest, for a maximization problem, value of f of x on our feasible region. So these give us our optimal solutions. And then the second thing that we're doing is we want to actually find our optimal value. So that's f at these specific x star points. So the first thing is to find your optimal solutions, which are your x values. And then once you find that, you want to find your quote unquote y value, which is your optimal value. And then you plug those optimal solutions into your function f in order to get that value. So I'm going to just show you a bit of the terminology that I was just talking about. So the points that minimize or maximize our function f of x on our feasible region, fr, are called either minimizers or maximizers, and they're also known as optimal solutions. So don't get confused between optimal solution versus optimal value. The optimal solution is your x value, whereas your optimal value is the value of your function f of x at your minimizer or maximizer. So if x star is a maximizer or minimizer, then f at x star is called your optimal solution. Okay, so that's kind of just a bit of terminology that we have to wrap our head around. So this is something we have to be aware of over here. So there may be more than one minimizers or maximizers, okay? So you might find more than one optimal solutions. However, there's only one optimal value. So that means that we're going to get potentially multiple candidate solutions, so optimal solutions, and they're all candidate, and then we're going to plug those all into our function f to see which is going to be truly our optimal value. And again, that depends if you're trying to minimize or if you're trying to maximize your solution, because it's possible that you may have more than one local maximums and minimums, maxima and minima. So that's a bit of terminology. Now we're going to go into our Lagrange multiplier. So this is really the basis of our theorem. So Lagrange multipliers, we use this, like I said, when we have constrained optimization problems. However, we also can use this when we have non-linear problems that we are trying to optimize. There's other optimization methods such as simplex method, for example, but a lot of that is linear programming, which require both linear objective functions and constraints, whereas Lagrange multipliers allow us to expand our definition and try to optimize problems that have non-linear values. Okay, so solving the optimization problem reduces the critical points of the Lagrangian function, and this is the Lagrangian function right over here. So we'll highlight that in yellow. So essentially what we are trying to do is we set up this Lagrangian function that I'm highlighting right over here, and the Lagrangian function is denoted as L, and it has two variables here, x and lambda. And then it's equal to our objective function minus the sum of the product between lambda and our constraint functions h. So again, solving the optimization problem reduces the critical points of the Lagrangian function, which is denoted here. So these numbers, scalars, lambda, this vector of lambdas is a vector of a new variable called Lagrange multiplier. So lambda in this case here is not an eigenvalue, it is our Lagrange multipliers. So we have to introduce this into our Lagrangian function in order to complete our optimization problem. So let's just take a note over here. So let's look at this. So the Lagrangian is a function that on n plus p variables. Remember where n is the number of independent variables x and p is the number of constraint functions. So how many h functions or constraints do we have? And its gradient is given by this right over here. So I do have previous videos on gradients. Essentially, you take the gradient, it's the collection of partial derivatives when you have multivariable functions. So here we're taking the gradient of our Lagrangian, and that's this function right over here, and we're going to set this to 0 and solve for our optimal solutions. And if you think about analytically solving simpler polynomials, this was a similar thing that we would do. We would take the first derivative, set it to 0, solve for x, and those would be your critical points. Now we're just doing this on a multidimensional scale, also when we're subject to constraints, but that general process is pretty similar. So if we look at some details here, we see that the column vector, which is the gradient of f minus the sum of our Lagrange multipliers multiplied by the gradient of our constraint functions, contains the partial derivatives with respect to x1 to xn. So this first piece over here is going to be a column vector on its own, which I've just defined. And then the second part, our h1 to hp, these are going to be the partial derivatives of the Lagrangian with respect to our Lagrange multipliers, lambda 1 to lambda p. So again, the first part over here, we're taking the derivative with respect, partial derivatives with respect to our x's, so x1 to xn. And then this second part over here, we're taking the partial derivatives with respect to our Lagrangian, so Lagrange multipliers, so lambda 1 to lambda p. Okay, so that's a little bit over there. And now let's dive into the Lagrange multiplier theorem. So these are the necessary conditions that we must have in order to compute this optimization problem. So the theorem is as follows. So if x star, which is an element of our feasible region, is an optimal solution of p, and recall p is our optimization problem that we defined at the beginning, and we have the vectors, the gradient of all our constraint functions, are linearly dependent, so independent, so if all this are optimal solutions and our vectors of our constraint functions are linearly independent, then there are unique numbers such that the gradient of our Lagrangian equals to 0. Okay, so what does this mean? So this is our theorem. Let's kind of dive into kind of what this means. So if we take the gradient, which is essentially the collection of partial derivatives of our Lagrange function, and we set it to 0, then we can find our critical points or optimal solutions x star, and these are candidate solutions for our optimal value. Okay, so let's have a little bit of a discussion on this theorem. So if p equals to 0, then there are no constraints, right? Because we have our h functions, which are constraints, h1 all the way to hp. And if p equals to 0, then we have no h functions, we have no constraint functions. So that simply means that our Lagrangian function, it just equals to f of x. And that means then our feasible region just equals to D, which is that open region, which is the subset of R to the N. Secondly, if our optimal solution, x star element of D, is a maximizer or minimizer of f of x, then the partial derivative of f at x star equals to 0, right? Because if you take the first derivative, which is here the gradient, which is the collection of partial derivatives, at those optimal solutions, then the gradient at that point is going to be equal to 0, right? That's kind of the whole discussion that you want the slope of the tangent to be equal to 0 if you're trying to get a maximum or a minimum. Next, number 3, which is our equation right up here. defines a system of n plus p equations with n plus p unknowns. So that's kind of a basis of algebra, that you must have at least you must have enough equations that equals to the number of variables in order to solve the solution. So if you have 2 unknowns, then you need at least 2 equations. If you have 3 unknowns, then you need at least 3 equations in order to solve your entire system. So here this provides us that very situation where we have n plus p equations and n plus p unknowns. That means we're setting ourselves up to find solutions. So next, solving this equation gives us all the vectors x star, and some of which are the optimal solution of our program. So like I said, there will all be candidate solutions, but from that list of candidate, we can use that to find our optimal solution. And often, like I mentioned, we will be dealing with non-linear problems, and this can create more complicated solutions, so it's just a little bit more computationally intensive to solve. This is a big thing to note over here, that if p is bigger than n, so if we have more constraints than independent variables x, then the gradient of our constraint functions are always going to be linearly dependent. So this is a problem for us. So if they're linearly dependent, then we cannot apply the theorem, the Lagrangian theorem, to solve them. The theorem only finds those candidates or critical points, x star, for optimal solutions where the gradient of the constraints are linearly independent. Okay, so in order to use this Lagrangian multipliers theorem, our constraints, the gradient of our constraint functions must be linearly independent. So that's not to say that there are no optimal solutions when you have linearly dependent constraint functions. However, you must find these solutions by other means, not using the Lagrange multiplier theorem. Okay, so that is the theory behind Lagrange multipliers. I know that can be a bit heavy, but I just wanted to give this to you so that you can have this in your notes. In my next video, we're going to go through an entire step-by-step example. Be sure to watch that because it will clear things up greatly. Sometimes theory can be a bit confusing, but the example will take you through the whole process, how to set up your Lagrangian function, how to take its gradient, solve for your x, and find your optimal solutions and your optimal value. So be sure to stay tuned and subscribe for more. I'll see you in the next video.